So welcome everyone to this machine learning coffee seminar. And today we have a very exciting talk by Vikas Garg, who is a recent machine learning professor at Aalto, Department of CS, who is going to talk about generalization and representational limits of graph neural networks. And if you have any questions during this talk, you can either write them in the chat or raise your hand, and then I will forward them to the presenter. So please, Vikas.
Thank you, Marcus. It's great to be here, and good morning, everyone. As Marcus asked, if you have any questions, please feel free to interrupt at any point of time. So I should mention this is joint work with Stephanie Jagelka and Tommy Yakola at MIT. And this is a very fascinating field, the graph neural networks, and there is tons of research going on in this area. In fact, if my stats are correct, this is probably the hottest area in the entire machine learning in terms of the number of papers and at NeurIPS and ICML recently. So I hope some of this stuff is exciting to you, and please feel free to get in touch with me after the talk at any point via email or any other medium if you want to discuss anything related to this further. Okay, so we encounter relational and interactional data in our day-to-day lives. This data takes various diverse forms. For example, it could be the actual 3D interactions. For example, in the context of molecules, you have actual 3D objects, and there are these atoms, and there are interactions. There are also these functional groups, and we have all kinds of interactions there. There are interactions between interactions within the molecule, and then there are interactions with the surrounding medium as well. The other important application is the internet. For example, you have multiple machines scattered all over the world at different locations, at geographically different locations, and files are being exchanged between these machines. This is more interactional in nature. In these interactions could also be semantic. For example, you have these, we have the codes or the programs, and there are these different modules, and these modules exchange, for example, certain variables or certain parameters, or they call each other. So the flow that we have, for example, in the programs, that could also be modeled very naturally. There could be even more subtle kinds of interactions. For example, consider the United Nations. You have these different countries, and they vote on certain resolutions, and each country is trying to persuade the other to vote for them. So now the nodes are in some ways the countries, and the edges represent the influences or the interactions that they have with subsets of other countries. So in some ways, this is nice because graphs provide us a unifying way of formulating and understanding these different scenarios. And so from a machine learning perspective, we are typically interested in the prediction tasks, as you might know. And so a natural question arises: what are the kind of prediction tasks that might be of interest to us? So here I would talk about three main tasks that have found much use within the community, and these tasks are very prominent in terms of the amount of research effort that has gone into analyzing them and using them in some applications. The first task is the graph prediction task. So here we are trying to predict a property of the graph as a whole. So for example, you have this graph molecule, and what we are interested in is predicting whether this molecule is soluble in certain media, or what's the bioactivity of this molecule. So we are interested in an overall property of the entire graph. The other kind of application is regarding the link prediction or the edge prediction. So here, one typical application is the product recommendation application. So you have two sets of nodes here. One is the product, and the other is the people. So you have some persons, that those are the nodes, and the other one are the products that they might be interested in buying, for example. And now an edge from a person to a product indicates that they bought this product. And now what we are interested in is predicting whether some customers or some potential customers or some persons who've not bought these any of these products, what are the products that they are likely to buy. So we are essentially trying to predict the missing links in some ways. And the contextual information that we have is that people influence each other. For example, these people might be connected on various social platforms such as Facebook, Twitter, and once they get to know about the others, those interactions might influence whether they decide to buy a certain product or not. So this is an edge prediction task. So we've seen so far the graph prediction task, the edge or the link prediction task, and the third prediction task is related to the nodes. So for example, consider this problem of protein design. Here what we have is we are given this 3D structure. Think of it as a scaffold, and what we are trying to predict is to label each of the node in this structure with one of the 20 amino acids. This is a hard problem in general because these proteins are known to be extremely brittle structures. So if you even make some local changes, they might often break down. And so the idea is, could we use machine learning on graphs to be able to do a good job at this task? Could we predict or label the nodes, predict the label for each node, and hopefully get structures that are stable? So this is a very expensive process in general if you try to do it via traditional methods. So there is lots of scope even in this. There are other important applications also. For example, you could think of a task which is graph to graph translation. Here, for example, the initial graph could be some molecule with specific properties, and then you might want to improve on it and try to get a better molecule. So that would fall under, for example, a graph to graph translation task. But by far, these three are the most important tasks. Okay, but before we can predict or do something useful with graphs, there are certain challenges that we must overcome. Not that graphs are in some sense very heterogeneous structures compared to sequences or grids. In case of sentences, for example, there is a natural ordering, from left to right in English when you have a sentence. Likewise, in case of images, you also like typically you could think of it as a left to right and top to bottom as you scan like the images. Mm, but there is no such natural ordering in the context of graphs. Typically, we are not told, like, there is no specific semantic directions to assign, unless it's like, for example, a 3D molecule or something, some very specific case where some kind of information is available. And also the another challenge is regarding the node degrees. In case of sentence, for example, that to each word you could assign a word to the left or to the right. Um, uh, and then the node degrees are essentially just, in this case, 2 for the words at the middle of the sentence. On the other hand, and likewise in case of images, that every pixel you can find the north, south, east, west, and northeast, and all these directions, other than the points probably near the periphery. So you essentially know that the degrees are more or less the same for image pixels, the different image pixels. This is not true in the context of graph neural network, in case of graphs generally, because different nodes could have completely different node degrees. So this is another challenge that we must somehow overcome. Okay, so graph neural networks are state-of-the-art models for embedding graphs into the vectorial spaces, into the real spaces. And these are parameterized models, and these can be specifically tailored to the end task. So I mentioned some tasks where these could be useful. So graph neural networks give us the ability or the flexibility to be able to do something which is meaningfully geared toward the end task. The general working of a graph neural network can be abstracted as follows. You have an input graph, and suppose your graph neural network consists of T layers. In each layer, nodes exchange messages with their neighbors. So each node in parallel exchanges messages with their neighbors, and based on this, the nodes update their current embeddings. And so you start from the initial features at the nodes. For example, these for an atom, these could be the atomic number, and so on. And now at the next step, you will aggregate in some sense, the combine the embeddings of your neighbors. You have your own embedding from the previous time step. You combine them in a semantically meaningful way, and you keep on doing this thing over and over again. You unroll the graph neural network for T layers, and at the end of it, you will have refined embeddings. And now using a readout function, you can combine these node embeddings. For example, your readout function could simply be the average function or the mean, the element wise max or mean operation. So this way you get a single embedding for the entire graph by combining the individual node embeddings that the graph neural network gives you. And this vector for the graph that you have, it could be used for prediction, because now you could use this vector to predict, for example, the property and see how well you are aligned with the ground truth labels that you have. So this is the general framework, but there are more specific, there are several specific instantiations. And for example, there is a graph convolutional network, which in some way generalizes the standard convolutional or the CNNs. Then there are the graph attention networks. There are graph isomorphism networks. So there are different kinds of based on how exactly you define your update rule, there are different instantiations that have been proposed and have found much success across several application domains. And these references that you see here, these are some of the earlier works in this space. Okay, so here is the agenda for today. We will first, the talk is divided into two parts. First, we will discuss a bit about the representational limits of GNNs. Here, from a learning perspective, what we would like is graphs that are distinct or that are non-isomorphic to be assigned differently to be assigned different vectors. I mean, if they are overlapping, if you are assigned the same vectors to non-isomorphic graphs, then that means these graphs might have different properties, but you are going to make the same prediction if they have the same representation. So here we are interested in somehow understanding what are the limitations of this standard GNN paradigm that I introduced, specifically whether these GNNs can tell certain graphs, certain non-isomorphic graphs from one another. The second,
Vikas,
sorry,
we
yeah.
have a question from the audience. So Oleg is asking if the embedding includes graph properties, for example, directions.
So graph properties we will abstract in terms of the labels. So you should think of graph as the feature, as a generalization of the feature vector. Each node has the features, each edge has the features. And now what you have is, so you could think of it as a structured space with features associated with nodes and edges. And properties you could think of as, for example, being expressed via the graph label. So this would be the analog from the standard setting. We'll go into reasonable detail into this. So just wait for a bit. The second part would be regarding the generalization guarantees. So we are, as I mentioned, our task is from a machine learning perspective, we are typically interested in predicting or doing well on the new data, on the test data, the kind of data that we've not seen previously. So we are not just interested in working with the training data and just trying to get like representation, doing a good job in terms of separating data, for example, from the training set. So a natural question is, how well can we predict? And so we will see how we get the first data dependent bounds for the graph neural networks. The focus of this part is essentially to say that how well can GNNs learn when they in fact can. So in some sense, first part, the representation part is regarding the limitations, and the second part is suppose your training proceeds well. So if your data is of the form that can be, if your training data can be fit well with the graph neural network models that you have, how well this class of models generalize to new data sampled from the same distribution. Okay, so let's dive right into the representational limits. This is the first part of our talk. Before going further, it would be useful to understand a bit more closely the functioning of a graph neural network. So let me give you an example. Consider a graph of 5 nodes, and let's see how the embeddings of node A evolve as we proceed through the graph neural network. So I am here assuming that the graph neural network is two layer deep. So you have 2 layers here. As I mentioned previously in passing, uh, consider the final embedding of node A. So this is represented by H subscript A at time 2. This embedding depends on the embedding of node A from the previous time step, as well as the embeddings of its neighbors. So the neighbors of A are B, C, and D. So at time 2, or at the final time step, A takes the embeddings of its neighbors from time 1, and it has its own embedding and feature vectors in the initial feature vector, and it uses that to update or refine its own embedding. Here, the gray box that you see, this is essentially an aggregation operation. So this could be think of as a parameterized, as the parameters of the model, or the weights that you are trying to learn as part of the training. Now, in turn, the neighbors of A, which are B, C, and D, they their embedding at time 1, it depends on the embeddings of their neighbors from the previous time step, which in this case is at time 0, when we just had the feature vectors for the nodes as their initial embeddings. And so if it were more layers, then this same procedure is repeated. Now, there are different formulations depending on whether you share the weights across the layers or not. If you share the weights, you essentially have analogs of recurrent neural networks in the context of graphs. If you don't, then you have what are called the stacked graph neural network formulations. So in some sense, you could specify this evolution of the embeddings for the different nodes in terms of 2 operations, aggregate and combine. The aggregate operation at time t plus 1 for a vertex V takes the embeddings of its neighbors from the previous time step t and combines them. This aggregate operation could be, for example, a sum operation. So you simply sum the embeddings of your neighbors or average those. So there are multiple possibilities there. And then once you have this aggregate from your neighbors, you can combine it with your own embedding or your initial feature vector to get a refined embedding. There are multiple rules here that you could implement possibly under this combined rule. For example, you could ignore the feature vector altogether, or you ignore the previous embedding of yourself. So each node just updates based on its initial feature vector and the current embedding of its neighbors. And these give different kinds of updates. These are mean field update rules. Then there is a loopy BP analog. So I would not go into the details, but suffices to say that these rules have their foundations in some ways in the graphical model literature. Okay, for our purpose, the important thing here is that why this is nice, because by expressing this evolution of embedding in terms of what we will call a computation tree, we get tractability about what's going on regarding how a GNN works. So, for example, for node A, we have this tree, this rooted tree. The tree is starting from the flow of information is bottom up. So you could think of as the leaves containing the initial feature vectors. And at each subsequent time step, we know how how the embeddings are defined. Likewise, we will have a computation tree for each of the other nodes as well. So for our example, we will have 5 computation trees with the root indicating the node that we are tracking. And once we this is nice because what it gives us is a way to work with the embeddings, because we could simply take the root embeddings and combine them via a readout function. So this readout function could again be, for example, a sum. So what we have essentially, to summarize, what we've seen is we can we can track the evolution of the embeddings of each node, and we know when a graph neural network operates on an input graph for a particular node, how would its final embedding look like? Because this is just the embedding of the root that we get from the computation tree. And likewise, once we have these embeddings for each of the nodes in the graph, we could just combine them together to get an overall embedding for the graph. And so this is a very simple procedure here. Okay, so now there are, why do we care about the properties? So I talked about the representational part, that we are interested in telling one graph from another graph, which is distinct. Why do we care? And so here is an example. So these are some very common drugs like paracetamol, penicillin. And here, if you look at their structures, there are different patterns which are very important. For example, the number of cycles, then the length or the diameter of the molecule in terms of its graph. Also, the presence of conjoint cycles. So conjoint cycle is a structure where two cycles share a common edge, and so on. And these are really important in determining the properties of the molecule. For example, what would be the behavior of the molecule? And so what we are interested in, it's natural to ask the question that given that we have two distinct graphs, for example, the molecular graphs that have different different patterns, we would expect a graph neural network to, or any machine learning method for that matter, to be able to tell them apart. Because if we are trying to do something meaningful with that, we better be able to do this task. So what we do is we abstract such patterns or important structures within a graph in terms of some important properties, like shortest or largest cycles. Like, so some of the, you might know, like they use the term girth for this. Then the diameter, radius, the number of cycles, to know whether there are some strongly connected components or fully connected components like cliques, conjoint cycle, etc., etc. As I said, graph neural networks are very powerful models. In fact, they are state-of-the-art models for embedding graphs. So you would expect that they do a great job at doing at separating graphs that differ in these properties. But unfortunately, it turns out that that graph neural networks that have a permutation invariant readout, they fail to distinguish certain pairs of graphs that differ in these properties. So you see this word permutation invariant readout. So let me tell you what it means here. A permutation invariant readout would be, for example, a mean or a sum. So the order of the nodes does not matter. That's all it means, that once you get embeddings for the different nodes, you apply a function that does not depend on the order of the node. So for example, if you apply a sum, it does not matter in which order you treat the nodes. And likewise for the average function. Okay, so let me give you some intuition into how we go about analyzing.
Vikas, I have actually a question.
Yes.
Does this result apply to sort of arbitrary graphs, or what about planar graphs? So if we restrict ourselves to graphs that can be represented in 2D plane.
That's a great question. So here, first of all, this is a worst case analysis. So there would be some graphs where you would be able to, and there would be lots and lots of graphs where you would be, graph neural networks would be able to separate them or tell them apart. Here we are interested more in a worst case analysis in some ways, that there exists some pairs of simple graphs or graphs with these properties that cannot be told apart by any graph neural network, regardless of the width and the depth, regardless of the embedding dimension, as well as the number of layers that we use. And the hope here, and the reason we are interested in studying this, is perhaps this will give us some insights into designing more powerful variants that could work around these using these counter examples as motivation. We could perhaps build more sophisticated models that have richer representational power in some ways. And that's the reason why we would like to analyze this. So here is an example construction just to motivate why why graph neural networks fail. So these graphs, consider these two graphs. One consists of two components, which are essentially two triangles. The second graph is just a single cycle of length 6. Clearly, these graphs differ in the number of cycles. For example, first graph has 2 cycles, the second graph has just 1 cycle, and so on. Now, I claim that the standard graph neural network paradigm that I introduced previously, it cannot tell apart these two graphs. Okay, so how do we argue about that? Here is a simple idea. Consider any node in the first graph. Let's just take this node B from the first component. And let's fix the depth of a graph neural network with arbitrary parameters. So let's say take the depth to be 2 or 3 or whatever, just fix it to something. Now, as I said, the evolution of the embeddings of this any particular node can be traced in terms of a computation tree, having that node as the root of this tree. And so for B, we sketch this computation tree, and the depth of this tree would be equal to the number of layers that you have in your graph neural network. Now, I can show a second node. I can find a corresponding node in the second graph, which is indicated here, which has the identical computation tree. And these trees would be identical no matter what depth you go to. So if you have a common graph neural network model that you've trained, and these two graphs are, you feed these two graphs into this graph neural network, with respect to node B, you will have identical embeddings. Why? Because at the leaf level, they had the same feature vectors, and now the update rules are same. So there is an invariant that you get, that after every time step, the embeddings that you will have for the node would be the same. Moreover, this holds not only for this one node, but you could show that for every node in the first graph, there is a corresponding node in the second graph, which has this behavior that the computation trees are identical. So in summary, what we essentially get is we get a multi-set of computation trees, which express the operation of a graph neural network on each of these graphs, and these multi-sets are identical. So there is no way, if you use a permutation invariant readout function where you get the embeddings of these roots. So so the argument is like this, that the computer for there is a bijection between the two graphs in terms of their computation trees, and the embeddings that we are interested in, which are the final node embeddings, they are simply given by the root of each computation tree. These embeddings are identical. So if I apply up any permutation invariant readout function, I won't be able to tell one from the other. They would summarize the graph vector that would result from applying a permutation invariant readout function would be identical for both graphs. Any questions at this point before we move forward? Okay, so I'll proceed. So I must mention there have been more powerful GN variants that have been proposed. So one of the things that you would have noticed with the standard paradigm that I introduced is that we aggregate in a very uninformed manner. In a way, we do not weigh we do not really distinguish between the neighbors of a node. So we simply say that, okay, you take the embeddings for at each time step, you take the current embeddings of your neighbors and apply an aggregate function, which is an unweighted aggregate function. For example, if you take the sum or the mean or the unweighted mean. So it turns out that by differentiating between your neighbors locally, so for each node, if you assign a port or a number to distinguish between your local neighbors, you can build more power into your model. So you could have aggregate functions that also take into account the number from which a message arrives. So or the neighbor that sends the message. This probably gives you more power than the standard model, because now you can intuitively what you can do is you can send pointed messages to different neighbors rather than locally broadcasting the same message to uh, all your neighbors. And likewise you can receive different messages, and so to cut the discussion short, you can differentiate neighbors based on their port numbers, and this is probably more powerful than the case where we ignore who sends the message to a node. Another and so like let me just say how this helps. For example, here is an example where by using the port numbering or assigning different neighbors to each of your neighbors, you can tell apart one from the other. So in these two graphs, for the node D2 in the second graph, it receives message from node C2 from port 2, while it receives message from node B1 from port 1. This is for the second graph I am saying. Whereas in the first graph for the corresponding node D2, the port numbers are switched. And so now just because your aggregate function takes into account the port number, you can tell that these are distinct just after one layer. So this is how port numbering helps. There is another graph neural network variant which is specifically designed for molecules. And here the idea is that because you have the 3D structure which is given to you, so you could first embed the edges which are bonds in this case, taking into account their angles with the other bonds in the vicinity. So you can measure the local angles and distances. Once you've embedded the edges, then you can find an embedding for the node by simply taking, for example, the sum of the edge embeddings that are incident on that node. And so this also probably helps, because now you are able to better tackle symmetries within the graph just by noting the angles and the distances locally. So it turns out that despite building more richness into your model, there exist certain port numberings that cannot distinguish between graphs that differ in some of these properties. And likewise, you can construct counterexamples for the DimeNet model also that works on the 3D model. So I would not go into the details because of time constraints, but the idea would be, for example, in the context of 3D graphs, would be to embed them on a cube now instead of the plane. So the um, cube helps you in some ways to argue about the local angles and distances in a more meaningful way. And there is also something nice that you can show here. For example, rather than having to explicitly construct a bijection, like I mentioned in a motivating example, how there were two graphs that we could not tell apart because of having similar multi-set of computation trees. We introduce a new proof technique that allows you to bypass this construction and argue in a more natural way using only some local transformations. So I would not go into the detail, but I encourage you to check the paper if you are interested. I should mention some open problems or active areas in this space. First of all, as I mentioned, first of all, I talked about consistent port numbering or local port numbering in these more sophisticated CP and GNN models. Numbering matters in these models. So I presented this example where I argued that these two graphs can be separated by due to this numbering. But then you can also come up with an ordering where they cannot be distinguished. So here, even with the consistent port numbering, you have these. You can come up with certain orderings which give identical embeddings for each node, and thereby with a permutation invariant function to the entire graphs. Um, so now the question is, how do we inform a good numbering? Now you have exponential number of orderings that you could do, because essentially you could permute the orderings locally, and then you have it independently for each node in your graph. So you're really operating in a huge space. But how do you inform a good numbering? This is not clear a priori, and the CPN GNN paper essentially bypasses this question. So for you, those of you who might be interested, this could be a good research question to look into. Uh, the other question is a more perennial one. Here, what we are interested in is designing more powerful GNNs. How do we build more sophisticated, more powerful graph neural network models that circumvent some of these constructions? And we sketch some possibilities in the paper. For example, you could go beyond your immediate neighborhood and take into account the local spatial features. For example, the angles between the planes locally in the context of molecules, and that probably helps you avoid some of the issues we saw with the standard model. There is lots of activity going in this space. These are some of the recent trends. First of all, people go beyond local neighborhoods by using so-called higher order graph neural networks. And here the idea is uh, that rather than restricting each node to updating based on embeddings from its neighbors, you form all k tuples or all k subsets of the nodes, and this gives you a more global perspective. You get information that is not accessible just from the local context, and probably builds more powerful at the expense of more complexity, obviously. There are other works, for example, graph neural networks for dynamic graphs. So you don't assume that your input graph is static. The edges could change, for example, across different time steps. So there is some work emerging on that aspect also. I also talked about the strategic setting as an example for interactional data. And so here the idea is to be able to build intelligence into the model by saying that your nodes, rather than being passive entities, they are, for example, strategic agents that are capable of making decisions locally. And so you need much more, the aggregate rules and the responses could be way more sophisticated. So these are some of the recent trends in this space. Okay, the second part. Now let's jump into the second part, which is going to be very short, and this regards the generalization bounds. Um, so a typical prediction pipeline in the context of graph neural network looks like this. You are given a training set. This is simply a bunch of graphs and graph and label pairs. So you have a graph and the corresponding property which you abstract in terms of labels. So your graph could be, for example, a graph pertaining to some molecule. Label could be some property, whether it is soluble or it is toxic, and so on. And now we fit a model from our family of graph neural networks. So which essentially means that we are trying to learn model parameters using this training data. And once this training is done, we are primarily interested in the test phase, at which point a new graph is sampled from the same distribution as the training data. And we would like to predict the label for this graph. And now the question of generalization is, how well can we predict on these new graphs? And so this is the task of generalization. So we consider the following setup for graph neural networks. We will focus on the mean field updates. So there is a standard result that for any permutation invariant aggregation function, provided it's continuous and some other major theoretic considerations, you can express it in this very nice sum decomposable form. So you see here a function which is raw, and in the parentheses you have sum. So any permutation invariant aggregation function or any permutation invariant function can be expressed in this form. So this is a known result from previous work. We will consider this mean field update, which has found to be extremely successful in the molecular applications, and that's the reason why we are focusing on this result. The setup is like this: each node makes a binary prediction by using its final embedding, the embedding that it gets from the graph neural network, and then the graph label is taken to be the majority of these binary predictions. So this is in some ways you could think of each node as, for example, being being an agent that makes a decision. So each of these could be using, for example, a local classifier, and they use it to make the prediction. And we assume that the generative process is as follows. Once you have these individual predictions, you predict the overall graph label to be simply the majority of these predictions. So it turns out that a standard result in learning theory, when ported to graph neural networks, says that the prediction error, or the ability of GNNs to generalize, can be expressed in terms of a sum of expected training error, how well you do on the training data, and a second term, which is the inherent capacity of your GNN class to predict label from the graph. For our setting, using computation tree as a tool, what we can show is that the second term can be replaced simply as the ability to predict label from a computation tree. Now, this is nice because in case of a graph, since the flow of information need not be unidirectional, you could have loops or you could have cycles. It's hard to argue about the capacity of a graph neural network to predict the label. Whereas, as I said, in case of computation tree, the flow of information is bottom up. So you have a unidirectional flow in some ways. And this is nice because now we can simply bound the error in terms of these individual computation trees, or the worst case computation tree pertaining to a graph, rather than having to argue about these possible cyclic dependencies in your data. And so there are most of the details are technical, but just to give you two quick insights about how this helps. Because we have the computation tree, we can recursively express the embedding for a node in terms of its subtrees. And so now you can express the embedding at the root in terms of the embeddings of the nodes that are root of its subtrees, and so on. And we know at the bottom layer we have the initial feature vectors. So this gives us a way to express the embedding at the root, which is nice. Second, we can show that if you do some small perturbations to the weights. So suppose you used a graph neural network and you trained a graph neural network and learned some weights. Now, if you perturb these weights slightly, for example, by adding some small, say, zero mean noise, the embeddings that you will get for the root of each computation tree would not change by much. And so essentially, this is nice because you get stability in terms of the embeddings for each of the computation trees. And this stability, and if you use, for example, a local binary classifier, which is norm bounded, then this translates into stability of your predictions, because the embeddings have not changed by much and you are using a classifier which is now bounded by a norm. So you can argue that the predictions that each of these computation trees makes would not change by much as well. And so this is nice, and this allows us to give the first generalization bounds for first data dependent bounds for graph neural networks. The dependence here is 1 over root m, where m is the number of examples, which is typical for such settings. Even data agnostic settings would give you a similar kind of dependence. For example, if you take the VC bounds, the dependence is almost linear in the embedding dimension and the max degree of each node, as well as the number of layers. To make these numbers, to make sense of these numbers, if you think of the recurrent neural networks as a special case where you operate on sequences rather than graphs, our bounds are very much comparable. And our bounds are also much better than the VC dimension bounds that don't take into account the margin term or the distribution of the data captured in our bounds via this term gamma. In particular, the dependence of VC dimension is cubic in the embedding dimension and linear in the number of nodes in the graph. Now, the max degree of any node could be substantially smaller than the total number of nodes in the graph. For example, for sparse graphs. So we are doing much better on both accounts.
Vikas, we are running out of time.
Yes, I'm finishing off. I'm finishing off in a minute. I'm almost there. Yeah, so these ideas can also be extended to the more sophisticated models that I presented, the port numbering models, and I encourage you to check the paper. The take-home message is that both representation and generalization are important. So far, the community has largely focused on the representational issue, which was to be able to build expressivity in your model so that you could distinguish between different graphs. But we believe generalization is a fundamental goal of machine learning. So just focusing on representation without bothering about generalization in some ways is meaningless. And so we should optimize in our models, we should optimize for balancing representation versus generalization, or expressivity versus generalization in some ways. And for more details, I refer you to this recent paper on ICML where we have all these details. Thank you.
Okay, thank you, Vikas, for a very interesting talk. Are there any questions we might have? Maybe we can take one question.
I have a question. Am I audible?
Yes.
Okay. Hi. I think you referenced the paper, How Powerful Are GNNs? And they have this Weisfeiler-Lehmann result where they argue that if two graphs are determined to be different by the WL test, then as long as the aggregate, combine, and readout level functions are injective, the graph neural networks can map these two embeddings to be distinct. I was wondering if your computational trees kind of would also be as powerful as the WL test, because there exists that gap between GNNs and the WL test. And do you see that sort of connection here?
So great question. There are two parts, I think, which needs some explanation here. So first, the model that you're talking about is called specifically the graph isomorphism network, where
Right.
and the idea there is that you can show that the standard paradigm is no more powerful than the 1WL test, or this is also called the color refinement algorithm for people who work in distributed computing. And the idea is that because essentially you could think of graph neural network as modeling the same process, that you take the feedback from or you note the colors of your neighbors, and then you update and if you do an injective mapping, which essentially means that you have an infinite amount of colors, practically speaking, that like every time you have a new color to hash into, then you essentially build the same power. So that's like a fairly straightforward result, I think. And now coming back to the question of computation tree, a computation or a multi-set of computation tree is essentially giving you all the information. In some way that you could think of it as a summary statistics, if I could use that term in the context of graph neural networks, because you are sketching the evolution of the nodes. So again, now when you are using the aggregate rule, you might, if you use the injective rules locally, like as you assumed in the case of graph isomorphism network, then you're building the same power intuitively. So, so all I'm trying to say is that by using the computation trees, you are not losing anything that graph isomorphism network or the models which were as powerful as 1WL had. So you are essentially, you can essentially mimic the same power here in the context of computation trees. Does that answer your question?
Yeah, I think that does answer one part of it, but also like, do you are you able to go beyond the 1WL test using computational trees in some manner, or is it that you don't lose out? Is that the primary benefit?
You will lose out if you go, like, for example, it's known. So 1WL is equivalent to 2WL,
Mhm.
but for for KWL, where K is higher than 2, and the idea is that you are no longer confining yourself to the local neighborhoods. You will form all K tuples of the vertices. So you'll get a hypergraph from the input graph.
Mhm.
And there are constructions there, so I probably don't have time to go into much detail. But then in that case, you are no longer confining yourself to local update rules, and it can be argued and it can be mathematically shown that KWL for K greater than 2 is provably more powerful. So the analysis that I showed here would not does not hold for those cases, because computation trees is still performing all the operations locally.
All right, thank you.
Okay, last question from Petteri.
Yeah, thanks, Vikas, for the great talk. Sorry to have missed the beginning. So let me just advertise a little bit, because all of this is actually connected to some extent to, of course, computation with symmetries and the graph isomorphism problem. And of course, in the theory community, we have at least good half a century of work probably on the graph isomorphism problem. And anyone, for example, interested in Weisweiler-Lehmann and related concepts should take a look at the survey that I actually pasted to the chat for everyone's benefit. I mean, it's in the most recent communications of the ACM by Martin Grohe and Pascal Schweitzer, who are basically two of the sort of young authorities on graph isomorphism at the moment. And I'm sort of hoping that we could actually get Pascal Schweitzer to talk at our theory seminar at some point.
That would be great. Yep.
Make sure to somehow cross-advertise this. And thanks again, Vikas, for the fantastic talk. And sorry that we're out of time, so I would love to have a little bit of more discussion here. But
yeah, thank you.
I
just wanted to give an overview of the field, because I think like lots of people are interested in the area, and sometimes because of the amount of research that goes in this area, it might be a bit intimidating where to start from. So I thought like it's perhaps better to give to discuss a bit about both representation and.
Of course, yeah, but just to point out the connections. So I think
sure. No, I think
important to somehow try
I think that's a great,
between areas. So.
That's a great question. In fact, like KWL and they all have their bases in distributed computing. Even the port numbering model that I mentioned, the consistent port numbering, this comes from the CPN, the CPNG, and it comes from the distributed computing paradigm, where we know how differentiating between the different neighbors